But the study of speech rhythm in Indian scenario has been very much less. So we will try to understand how speech rhythm can be categorized under the Indian scenario, and mostly we are working on low resource languages of northeastern region. So we'll discuss how we can classify the languages according to the rhythm class hypothesis that we'll discuss a little bit later. And then we'll cover time domain methodologies and limitations, and then we'll go to the frequency domain methods for speech rhythm assessment. And one specific section is based on rhythm format analysis, which you can see in the number 4 category here. Rhythm format analysis is comparatively a newer approach to look into the speech rhythm from the modulation spectrum and spectrogram concept. So we'll discuss rhythm format analysis in detail here, and we'll see some applications after that, where we'll discuss the methodology and the databases that are present, that are available, and we'll see some experimental results in the later sections of 6, 7, 8, and 9. Okay, so let me go to speech rhythm definition. So we all know speech rhythm. When we talk about music, we know that there is a rhythm is always present. So when we like a specific song, we like the rhythm of the particular song. And but we have not talked much about the rhythm that is present in our speech during our speech communication. So speech rhythm is a very fundamental aspect of spoken language, and it is basically referring to the pattern of the stresses. For example, by the word stress, I mean like when we speak something, we utter one word, we unconsciously maybe we are stressing at certain syllables. Okay, so we sometimes we stress more, sometimes we stress less at certain segments or syllables, and that particular pattern actually leads to the speech rhythm behavior. So we can say that speech refers to the pattern of stresses. It can also refer to the pause. When we pause between two sentences or two utterances, that can also be a part of the rhythm characterization. And also intonation in speech is there, so that can also contribute to the speech rhythm characteristics. So as we can mention, this speech rhythm is a part of fundamental aspect of spoken language, because from this speech rhythm, what we have understood or what we have analyzed is that speech rhythm can contain valuable insights. For example, these insights may be from for linguistic features, or in distinguishing certain languages, certain language families, dialects, then speech disorders also, and so on and so forth. So the platform is open, and we can see how speech rhythm can be beneficial in many speech technologies that are now being developed by various research groups across the globe. Therefore, so I come to the textbook definition of speech rhythm. So firstly, here we can see the term called isochrony. So what is isochrony? Isochrony is when we have equal timing intervals between stressed syllables or the mora, that is coming from the linguistic background. So we have syllable and mora in a particular linguistic element. So if we stress on the syllables, then that can lead to stress timed languages, or if we only stress upon the syllable present in the linguistic element, then it can lead to syllable timed, or if we have equal timing intervals between the mora, then it can lead to mora timed languages. So according to these three categories, stress timed, syllable timed, and mora timed, we can have three different language family. So the going to the second, just a minute. So going to the second point here. So languages were grouped by these three gentlemen, James, Pike, and Abercrombie. They uh, categorized the languages to be stress timed, and they found out that English is stress timed language because it has got equal timing intervals between the stressed syllables. Or it can be syllable time, that is the number 2 category, where we can have Spanish, French, etc. And lastly, the Japanese, which falls into the mora timed category. So I repeat here. So stress time languages are languages which have equal timing intervals. So duration is equal between the stressed syllables. That will be leading to stress time language family, or it will be having equal timing interval between all syllables, then it will lead to syllable timed, like the Spanish or French language. Or it may have equal timing interval between the mora. So it will lead to mora time, the Japanese Japanese is an example of the mora timed language family. Now, why it matters? It matters because ASR, TTS, language identification, dialect identification, pathological speech diagnosis, language acquisition studies, over all the linguistic studies, these applications can get benefited from the knowledge of the rhythm that is embedded in the speech utterances of the particular language family. So we can summarize that rhythm is multidimensional. It involves time, frequency, amplitude, and linguistic structure. Linguistic structure, we basically focus on the syllabic structure of the, or the grammatical structure of the particular language. So this slide again compares the stress time, syllable times, and mora timed languages. So stress time languages are, examples are English, Russian, Arabic, German, Persian. Characteristics are stressed syllables occur at approximately equal intervals. So the duration, when we count the duration of the stressed syllables, the syllables that we stress when we speak, so we compute the duration of the starting point and the end point, and we find out that the stressed syllables are having approximately equal intervals. So therefore we have a periodic pattern here. When we listen to or when we perceive, we get to have a periodic pattern. So that leads to the rhythmic behavior. And from the linguistic point of view, we have, when we have discussed or we have analyzed these particular languages like English, we have found out that they have common consonant clusters, or there may be some vowel reduction present. Whereas in syllable timed, we have these many languages like Spanish, French. So when they speak, the syllables occur at approximately equal intervals. So the syllables here, not the stress syllable, but all syllables. And there is another observation is that there are fewer consonant clusters and full vowel length is preserved. So last is the mora time. So here in the mora time, earlier example was Japanese. I'd also like to add that in the Indic languages, the Assamese, Tamil, Malayalam, Kannada, they all fall into the mora timed category, whereas Telugu falls in the syllable timed category. So mora is a subsyllabic unit. So mora are the timing unit where we have the equal interval or equal duration observation. So coming to the time domain rhythm matrix. So as I mentioned here, we all are basically concerned about the computation of interval. So you can see all points here. So interval means the duration. So ultimately we are more interested on getting the proper annotation of the consonant and vowel patterns in the particular utterances. So what happens in the earlier years, people were more concentrated over the time domain rhythm matrix. Time domain means here we are basically concerned about the computation of the consonant and vowel durations. So one block diagram can be seen over here. Is it coming properly?
Yes, ma'am.
Yeah. Okay. So we can see that here in this particular block diagram, we have the speech signal. Then we detect the vowel onset point and vowel end point, so that we can mark the mark, or we can get it annotated as per the starting point and the end point. And then we measure the vowel. V goes for vowel and C goes for the consonant. So we measure the vowel and consonant duration, and then we measure a certain metrics. Okay, these metrics are known as rhythm metrics, or RM in short. So rhythm metrics, and after calculating the rhythm metrics, we can classify or we can categorize the languages as per these three categories: stress time, syllable time, then mora time. So basically we are concerned about getting the VOP and VP of the utterances, and measure the vowel and consonant durations, and then we go to compute the, when we have the measure of the vowel and consonant durations, we can have different rhythm metrics out of these duration values. So let me go to the rhythm metrics. What are rhythm metrics? Rhythm metrics quantify the variability of vowel and non-vowel, that is the consonant, interval durations extracted from the speech. So this list shows the shows here there are 7 rhythm metrics. There are many more, but these are the most popular one. So number one is, first rhythm metric is percentage V. So it is the percentage of vowel duration. Delta V is the standard deviation of the vowel duration. Delta C is the standard deviation of the consonant duration. So you can see here, these are all the about the duration part. And then we have NPVIV. This is normalized pairwise variability index. That is for the vowel, because it is V here. And this is for the consonant, NPVIC. And then we have another one popular rhythm metric, that is called Varco V and Varco C, which are the coefficient of variation of vowels and coefficient of variations of consonants respectively. So what is the interpretation or the linguistic interpretation? Linguistic interpretation, percentage V, if it is higher, then we can say that the language is more syllable or mora timed. It is not stress timed. It is, if it is higher, then it will be more towards the syllable or mora timed continuum. And then if delta V is higher, then we can say that the language has more durational variability. If it is delta C, then and if it is higher, then it will be delta C, that is for consonant. So it will have more stress time tendency, which is the complementary to the earlier one, delta V. So on and so forth. So you can go through the NPVIV here. If it is higher, then stress time. If that NPVIC is higher, then we have greater consonantal variability. Varco V is rate normalized percentage equivalent, and Varco C is rate normalized delta C equivalent. So these are some of the formulas that we generally work on. Percentage V is sum of all vowel durations. We take the all summation of all the vowel durations out from our annotation markings, and then we divide it by the total utterance duration, and then multiplied by 100 for normalization, and it will lead to the percentage V calculation. And we can see here, if it is high percentage V, then the language is syllable or mora time. So this research has been there over the last 20 or 15 years, and those who are basically the part of the time domain rhythm assessment. So delta V is similarly sensitive to speech rate, and how we calculate that, we take the standard deviation of all vowel segment duration after we do the annotation properly. So Varco V is the standard deviation of the vowel durations, and then mean of the vowel duration divided into 100. So these rhythm metric formulas are available, and we can compute them according to our annotation parameters. Now there are some limitations of time domain metrics. So what happens here? You can see the this calculation in this block diagram, you see this whole calculation has one limitation because it has got a problem in the detection of VOP and VP. If we detect this VOP and VP wrongly, then the entire rhythmetric computation is affected. And it is also detection of VOP and VP. If we do manual annotation, then it is also subjective to error as per the annotator or the linguistic expert who is perceiving the recordings and who is doing the manual marking. So what happens, time domain rhythm metrics are sometimes they are subjected to errors because they are giving different calculation according to the different who is the annotator. That is the thing. So limitations of time domain metrics is that rhythm metrics are facing serious criticism later on because manual annotation burden is there, that we have to do hand annotation of vowel consonant boundaries, which is extremely time consuming, where we have got a large database, so it will take lots of time to do manual marking of vowel consonant boundaries and then calculate the rhythm metrics. It is error prone, as I have already mentioned, and also it requires the linguistic expertise in the target language. So suppose if we want to study one language which is not our native language, and we want to do rhythm assessment, then we may not be able to do a good justice here because we do not have the linguistic expertise in that particular language. And linguistic expertise in low resource languages or under resourced languages are also very difficult to get this because there are very less population, and there may be some less number of linguistic experts there, so that may be causing one problem later on. Then language resource dependence is another problem here. Limitation is there. So what happens, we can go for automated methods like forced alignment models, but they exist for only few large group, high resource languages. So the example here I'm giving is from our Upper Assam region. So low resource languages like Mising, Deori, or Manipuri, they do not have such tools. So we have to rely on manual annotation here. So then isochrony hypothesis fails. So isochrony hypothesis was that the equal interval of stress syllable, equal interval of syllable and mora, this may not be always acceptable because duration varies with speaking rate. It can vary with stress. It can also vary with phonetic context, or it can, and of course it will definitely vary with the speaker time to time. Therefore, and no temporal dynamics are present over here. So how the rhythm evolves over time within the utterance, that is missed here, because these are all simple plain mathematical formulas. So speaker variability is a major problem. High interspeaker variability will make the classification unreliable with small corpora. So metrics overly sensitive to individual speaking styles. So this is another important point. And no frequency perspective. So no frequency perspective is, here you see rhythm is actually an oscillatory process. It is a periodic phenomena. So people were not looking at this, this point when they were working on this rhythm metrics, this calculation formulas. They were missing this particular point, that rhythm is actually an oscillatory periodic phenomenon. So time domain measures cannot capture the frequency content of the rhythmic pattern. So there was a very big or large research gap in the application of this time domain metrics. So Here I'm just giving you a glimpse of how these vowel and non-vowel characterizations are annotations are marked, and this is done through an automated method. And this is just to show you how the speech signal and how the marking of these vowel and non-vowel segments can be done, and that can be later used to do the rhythmetric calculation. Now, as I'm talking about the distribution of languages earlier, this is how the rhythm metrics were useful in getting the characteristics of the languages patterns. So you can see here, Spanish is, if we plot Varco V versus the NPVI VP plot, the 2D plot, then we'll see that Spanish is positioned here and British English is positioned over here. And as we have already mentioned earlier, here, English belongs to the stress time category and Spanish belongs to the syllable time category. So in this plot, we can see that, you know, British English is a stress time, then Spanish is syllable time. And in between, we have the Japanese, Assamese. So these are the Mora time. So this is how the characterization was done earlier using the rhythmetric plots. There is another figure here. Here we can see the plot of percentage V over here on the vertical axis, and this is the NPVI V. If we calculate and plot this percentage V versus NPVI V plot, we can also see a similar pattern over here. Spanish is at the corner here, and British English is at the corner here, and Japanese and Assamese, which are Mora time, they will be situated in between this stress time and syllable time. So the Spanish is the syllable time language, so it is here, and British English is the stress time. And here we can see that Dolu and Pagro, these are two dialects of missing language of the Upper Assam region, and which were not earlier studied. And in our study, in my actually PhD thesis work, we have categorized the missing language to be nearer to the British English. That means they are falling under the stress time languages. So any unexplored language, if you are working with any unexplored language whose rhythm class is not known, then you can work like this. You can compute the time domain rhythm metrics and you can see which category they are out of the three. That is whether they are stress timed, Mora timed, or syllable timed. Now coming to the frequency domain rhythm analysis. So here what happens, as I have already told you that rhythm is actually a periodic formula. It's an oscillatory phenomena. So what is the key insight? This is also based upon neurobiological research. Okay, so it is accompanied with neurobiological research, and this research, you can see the paper over here. This is 2012 paper, neural finding, cortical oscillations, phase lock to speech at 4 to 8 hertz and 1 to 3 hertz. This is one paper by these two persons who are actually neurobiologists. They have actually mentioned that the natural speech rhythm correlates with the low frequency oscillations, that is less than 10 hertz in the speech amplitude envelope. Okay, so all the years people were not looking at the frequency domain perspective, but actually we should look at the rhythm from the frequency domain perspective, because speech rhythm correlates with the low frequency oscillations, and typically it is less than 10 hertz of oscillations in the amplitude envelope. So this is a categorization how different information can be embedded in the low frequency region of oscillation in the amplitude envelope. So 0.5 to 0.8 hertz, we say that rhythm to be slow or discourse rhythm, and that is actually giving us intuition about the sentence phrase and the sentence boundaries. If we go towards higher frequency, 0.8 to 2.3 hertz, we are basically going towards the stress or foot intervals. So if we go up, then we can say that we can have the in the 2.3 to 7 hertz region, we can have the syllable rate information embedded in the speech rhythm. Then 7 to 20 hertz, that will go towards the subbit or phoneme information, and 20 to 50 hertz, it goes towards the formant transitions, that is a voicing, vowel identity, etc. So these are the findings from this particular paper, and based on such works, that is the neurobiological works, speech researchers also try to look at speech rhythm from the frequency domain perspective. So as I have mentioned earlier, it is being said that rhythm is encoded in two complementary modulation envelopes. So what are the two modulation envelopes? One is the amplitude modulation, AM, and another one is the frequency modulation, FM envelope. So in the AM envelope, what happens? What we do? We compute via absolute Hilbert and transform of the speech signal. Then we track the slow amplitude changes, that is vowel peaks versus consonant valleys. We try to capture the sonority contour of the syllable. And we find that during this 3 to 7 hertz band, we get to know about the syllable rate present in the speech utterances. And this information is key for identifying the vocalic prominence patterns. So from here, we understand the syllabic structure of the language as a whole. So what we can summarize is that AM peaks will lead to the vowel nuclei, and the valleys or the troughs will lead to the consonant and pauses, and they will ultimately give us the information about the syllable rate, and overall we'll get to know the vocalic prominence patterns. So these are from the amplitude modulation envelope. Going to the frequency modulation envelope, we all know that we can calculate the F0 contour, and then we can capture the slow F0 variations over time. And this F0 contour, that is a pitch contour, will be encoding the lexical tone, pitch, accent, and the intonation. However, it will break during the voiceless consonants and pauses, and it will complement AM, that is FM will add the prosodic linguistic information, that is because of the tonal information in the F0 contour. So AM will ultimately give us the sonority contour of the syllables, and FM envelope will give us the F0 or the pitch contour. And there are many algorithms that can be applied for computing these AM and FM envelopes. Now I'm talking about rhythm formant analysis, which is a newer technique which is developed by Professor David Gibbon. And RFA actually analyzes speech rhythm from the low frequency spectrum of both AM and FM envelope, that is the frequency range is limited with below 10 hertz. So why this RFA is important? Because RFA tries to get the natural rhythm calculation or the correlation with the regular low frequency oscillations below 10 hertz. And these are evident from the neurobiological resonance patterns. Number two is the assertion is that there will be simultaneous rhythm formants. Now I would like to mention that David Gibbon had coined a new term that is called rhythm formants, which is different from the formant frequencies. I will see in the figures in the later slides how these rhythm formants are depicted. These rhythm formants are actually the peaks present on the low frequency spectrum. So we can find that there are multiple rhythm formants. R formants are the new concept here. So R formants, they coexist in the low frequency spectrum at the same time, representing different rhythmic hierarchies like syllable, word, foot, phrase, etc. And number three, the third assertion is that Professor David Gibbon was that R formants will reveal the temporal sequencing of the rhythmic units, encoding how rhythm unfolds over time. It is not a static calculation like the time domain rhythm matrix, but rather a calculation which flows across the whole utterance. Then asymmetrical rhythm formant patterns are asymmetric across languages, dialects, speaking styles, so that will be working as a most prominent or most discriminative feature in the language technology. And the key advantage of RFA, for which the RFA is now being explored, is that RFA do not require any manual annotation, which was a problem in time domain rhythm metric calculation. So RFA is built in such a way that if you do not know the language, or if you do not have any linguistic expert, or if you are not having any manual annotation done in the particular language, even if all these things are missing, you can apply RFA directly. So because it operates directly on the acoustic waveform, so there is the manual annotation requirement is vanishing here. So how we calculate about this rhythm formants? We normalize the speech signal, we calculate the Hilbert envelope. It's a very simple program. So, and we smoothen it, then we calculate the FFT, we do the FFT, and we extract the 0 to 10 hertz range spectrum, and then we detect the magnitude peaks, which are now coined as rhythm formants. And please remember, these rhythm formants are not the formant frequencies. The formant frequencies which we talk about, they are having values higher than 50 hertz and so on and so forth, but these rhythm formants are only between 0 to 10 hertz. So this is the computation of rhythm formants from AM envelope. As I have already mentioned, we do the AM envelope computation and median filtering for smoothing. So you can see the AM envelope over here, which is the purple colored one. And then we do the FFT, and we can get the LF spectrum from 0 to, you see, the 0 to 10 hertz of range. And when we do the normalization, we'll find that here some peaks are present. So you can see the red dots over here. All these red dots are ultimately our new rhythm formants. And while doing so, here in this particular figure, we are detecting the first 6 dominant peak frequency. So these first 6 dominant peak frequencies are called RF1, RF2, RF3, RF4, RF5, so on and so forth. And if you are interested in RFA, you can go to the GitHub account of Professor David Gibbon. These are the step-by-step algorithm. And then, so I repeat here about the rhythm formants. So rhythm formants are the frequency values in hertz corresponding to the highest amplitude peaks, as we can see in the last LF spectrum figure. And they represent the dominant rhythmic oscillation rates in the speech. In general, RF1, which is between 2 to 3 hertz, as you can see here, this is 0 to 10 hertz only. So if the rhythm formants are between 2 to 3 hertz, then it will give you intuition about the word or stress rate. 4 to 5 hertz, it will give us interpretation about the syllable rate of the particular language and the rhythm. And then if it is around 6 to 8 hertz duration, then we can get the subsyllabic rate of rhythm. So these are the illustration of LF spectrum from AM envelope. I am giving here three figures. This first figure is for Pagro missing, that is one dialect of the missing language, and you can see the AM envelope over here. That is the dark blue colored envelope, and nearby side by side we have got the LF spectrum, where these red dots are the rhythm formants for the particular Pagro missing utterance. Then the second one is for the Dolu, that is the Dolu missing. Dolu missing is again, you can see the rhythm formants characterizations are these are here present, and this one is for Assamese language. The last one, the bottom one, is for the Assamese language, and you can see the rhythm formants are calculated, and here only the first 6 dominant peaks are calculated. So low frequency long term spectrum and detected rhythm formants are being shown in this particular figure. Next is from the FM envelope. So we have already seen that both AM and FM envelope below 10 hertz frequency, they can encode the rhythm formants or the dominant peak magnitude peak values. So these are the speech signal. Again, this is for Pagro missing, the first one, and this one is for Dolu missing, and this one is for Assamese. And then this is the FM envelope. This FM envelope or the for all these language varieties are calculated, and thereby we have generated the LF spectrum, and LF spectrum has showing the 6 dominant rhythm formants. And here we have only shown 0.5 second to 5 second of FM envelope for better visualization. Now we keep record of all these rhythm formants from both AM envelope and FM envelope, and we can explore them for discriminating the languages or dialects, or for various speech disorder applications that we are now doing research on. Now, I'd like to show how we do the qualitative research. The qualitative research is relating the rhythm formants with the word rate and the speech rate. So let me show you just one example I'm giving from Assamese. Here, these all 3 speech utterances are from the Assamese language, and we are calculating the rhythm formants in the LF from the LF spectrum over here for all these 3. These are for a single Assamese variety. Okay, from different speakers, different utterances are taken. And now if we do the qualitative analysis, we find that this rhythm value, the RF, these RFs, which are the blue colored RFs, these gives us the value of the word rate. Okay, we have done the calculation through perception test by native listeners, and they have these 2 values have agreed to our earlier analysis of the LF spectrum rhythm formant values. So we can say that these blue colored highlighted values are ultimately the inherent or embedded word rate in the particular speech rhythm, and this is the speech rate of the particular language. Now, coming to the spectrogram now. So we all know what is spectrum, and then if we do windowing process over here, then we can get the long-term rhythm spectrogram, sorry. So from here, what happens? We are calculating the AM LF spectrum. We are also calculating the FM LF spectrum that is coming from our first block. Then we are doing windowing process over here. We are applying windowing process so that we can have the AM LF spectrogram, and we are showing here the FM LF spectrogram. And if we embed, or if we concatenate this AMLF spectrogram RF formants trajectories, then such type of visualization is coming up. And using these visualizations, we can also do the discriminating feature research. Now, I'll skip this. So I'm repeating here. What we have done so far, we are discussing so far, it is that in the time domain rhythm metric, which was actually dominating the speech rhythm assessment for the last 20 years, has been now criticized and has been now is now going towards the frequency domain methodologies. So what has been the advantages of these frequency domain methodologies? Because they do not require any linguistic expertise, and we can actually see how the rhythm is encoded which is naturally a oscillatory phenomenon. So I'm showing results from our own research here. These are the rhythm metrics which are discriminating Assamese and Pagro missing and Dolo missing in this particular slide. So our key observation is missing shows lower percentage V and higher delta V, that means missing language has more consonantal um, variability compared to the vowel variability. Also, missing is having higher Varco V and higher NPVI V, which means that stress timing tendency is confirmed. That means missing is falling under the speech stress timed language family. Whereas Assamese is grouping near the Japanese on the rhythm continuum, and Dolu missing is rhythmically closer to Assamese compared to the Pagro one. And we have done this using we have validated the results with statistical methodologies like linear mixed effect models, and that confirm that the rhythm matrix differences are statistically also significant. Now we have done SVM based classification. So rhythm metrics are successfully, this is time domain rhythm metrics. So they are actually working as a distinguishing feature for classifying languages like Assamese and missing. So here you can see the baseline MFCC result and rhythm matrix, 7-dimensional rhythm matrix we are using. And lastly, we are using rhythm matrix 7-dimension plus the speech rate. And the best accuracy, we are getting 83.28% for Assamese versus Pagro missing when we apply the rhythm matrix and the speech rate as a feature set. This is for the time domain one. Now the proposed RFA features. So after we calculated the AM/FM envelope and their respective low frequency spectrum, we are proposing 3 new RFA feature out of it. That is called the number of detected peaks, NDP, then mean MFT, mean frequency of the detected peaks, and variance of the detected peak frequencies. And these various features are being applied to improvise the results of the language classification rate that was found to be only 83.28% for the time domain rhythm matrix. So I'm going to show the results here. And we have done SVM classification using LF spectrum features. So it can be applied on any new languages if you're working on, and you can reproduce the results if you're interested in the speech rhythm characteristics. So of course, the result is being improved up to 92.73% if we apply various combinations of rhythm form and vector and the proposed features. We are also applying DCT here, and then you can see the variations in the classification accuracy. Now, qualitative validation that we have done, we have found out that the first and the most dominant R format in the LF spectrum corresponds closely to the speaker's word rate. And for missing, it is around 2 to 3 hertz, and for Assamese, it is 2.5 to 3.5 hertz. Then syllable rate is the dominant R format aligns with the syllable rate in our particular language of this interest language. We are getting typical speech syllable rate of around 3 to 6 hertz within the LF spectrum 0 to 10 hertz frequency rates, and this validates the LF spectrum capturing the linguistically meaningful rhythm, not just abstract acoustic patterns. So it aligns with the essence of the natural speech rhythm. And discourse rate is sub 2 hertz rate, that is even slower speech rhythm patterns like phrase, clause, discourse level timing. They are also encoded below 2 hertz of the LF spectrum. and yet they are not yet fully explored for these new languages like missing. Now I'll skip this actually. Okay, so I'm within time. Let me. These are some statistical validation methods that can be used. If you're interested, you can go through these. Experimental findings are validated using the rigorous statistical test before classification. One is the linear mixed effect models. And then the wild chi-square test, that is a type 2. Then you can apply Bonferroni post hoc test, that is a pairwise test. Bhattacharya distance, the CHAP values, and the TSNE visualization, that is a 3D visualization. So these are different statistical validation methods that can be applied in getting the statistical validation for speech rhythm assessment methods. Now I'd like to come to the various applications of speech rhythm. So speech rhythm, this rhythm format has been rhythm, not only rhythm format, but the time domain rhythm metrics, which are the first category. They were also being applied in various time to time research. So there were a survey done, and in this particular survey we can see that there are Mora timed Indic languages. I'd like to list these languages. So under Mora timed languages, we have as we have uh, a huge audience here, so you can see your native language is falling into which category. So let me start with the Mora time language family. Assamese is Mora time, Bengali is also Mora time, then Gujarati, Kannada, Kashmiri, Marathi, Malayalam, Punjabi, Oriya, Tamil, and Telugu. Then syllable time is Hindi. Hindi is syllable time like the Spanish language. So syllable Hindi is a syllable time. That means there is lack of predetermined word stress. There is less stress in Hindi language. Then Dravidian language, the Kannada language children, they are they are showing Mora time, but this is only for the children. Generally, Kannada is Mora time language, but Kannada is for the children, that is 8 to 12 years. They are showing Mora timing in one research. Then Indian English. So when we have accented in Indian English, then Indian English is more syllable time compared to the British English due to the influence of the native Indian L1 languages. So we can also see the effect of L1 languages over the L2 languages. So that is also another research avenue that can be applied. Konkani is classified as syllable time. Goan Konkani has low NPVIV values, which is consistent with syllable time languages like Spanish. So these are the languages that I have found during literature review. And if there is any language missing here, that can be actually examined and can be seen which language class, rhythm class they are falling. So it may be of someone's area of interest. Then applications of speech rhythm analysis, why it matters for us as engineers or technologies. We have to understand the speech rhythm because it has got broad practical applications across many language technology as well as healthcare industry. So we can say that it can have implications on the automatic speech recognition performance. And rhythm features actually improve ASR for low resource languages where the data is scarce. Prosodic rhythm can help segment the word and phrases without transcription. That is number one. Then in the TTS research, rhythm models can control the speaking rate and prosody in TTS systems. Natural sounding Assamese or missing TTS needs accurate rhythm modeling. So we are working on it right now, how we can do rhythm modeling to get natural sounding TTS. Then speech pathology and diagnosis, rhythm abnormalities indicate stuttering, Parkinson's, dementia, and depression. Automated rhythm format analysis can assist clinicians in objective assessment of the disorders that are present in the speech signal. Then language and dialect identification, and low resource language technology. So low resource language technology is basically of importance because we do not have proper annotation. So annotation free rhythm features enable NLP for endangered languages and low resource languages without the text resources. So since endangered languages are having very limited population without much text resources, that on that languages we can apply these rhythm features and we can find out. So it is critical for Northeast Indian tribal languages also. So this is another area of research that can be focused on. Language acquisition research, rhythm analysis tracks how children acquire timing patterns of their L1 and useful in studying bilingual language transfer effects in various societies. Direction for future research, I'll go to another application that we have recently published in OCOCOSTA, that is RFA for Indic language classification. Here what we are doing, we have taken 6 Indian languages. Earlier RFA was not applied on any Indian languages, only results were there coming from rhythm metrics. So we are going to see if annotation free RFA features can distinguish these many Indian languages like Bengali, Kannada, Malayalam, Marathi, Tamil, Telugu, using only the low frequency spectral analysis without any deep learning or manual labeling. So what are the feature groups that were explored? It can from the rhythm formats, we are exploring the NDP, MFTP, VFTP, 4-DCT coefficient. So it makes up 14-dimensional rhythm features. Then spectral measures coming from the LF spectrum are centroid, spread, etc., roll-off, flatness. Then we are also taking the variance of rhythm formats and magnitudes, making up 24-dimensional feature vector, and 2D density of LF spectrogram, which is making up a feature vector of 4 dimension. And side by side, we can see the results of SVM classification. So what is our observation is that direct rhythm formats alone, they fail to categorize these languages, almost around 38%. So threshold and shape features are essential. So later on, moving towards the LF spectrogram, we can see that LF spectrogram, the temporal dynamics part, that is being showing greater result compared to the LF spectrum. And the best one is the all features combined. That is the accuracy 78.12 is coming, and this is totally annotation free. And FM feature, they dominate the CHAP top 15 individually, and 2D density 1 AM is the single most important feature. Application number 2, I'm just giving a glimpse of how RFA can be utilized. These are only 2 applications, and this was a part of our InterSpeech 2025 paper. Here RFA was used for dementia detection, and the data set that was used was Addresso Set Challenge, which is having 237 recordings, that is cookie theft picture description task, and it was later balanced by age and gender. And the key idea in this particular paper or the work was that dementia disrupts the speech rhythm, and we have no knowledge of how the speech rhythm gets disturbed or disrupted. So the key idea was, can RFA rhythm spectrograms can detect whether they will be able to detect Alzheimer's, dementia, and predict the MMSE cognitive score. That is the score that is one pathological score that is coming from the doctors. Whether that score can also be predicted from the speech signal directly. So while working on this particular research problem, the approach that was taken was that AM and FM rhythm spectrograms were computed using 5 seconds sliding window, and total 6 dominant rhythm frequencies trajectories were tracked over time, and later the variance features were calculated out of it. Then 2D DCT spectrogram were calculated, which will build up our spectrotemporal feature set, and later it was combined to get 30-dimensional feature vector per utterance, and SPM was used for classification, and SVR and decision tree for MMSE regression. And there is another approach that was reported in this particular paper, that is approach number 2, where we were doing the data-driven methodology, the AM/FM rhythm spectrograms, and their first and second derivatives, they were all being put to the vision transformer, and this speech where the BART was extracting the 768 dimensional linguistic embedding, and the dementia class was getting detected. So here only 3,774 trainable parameters were there. There was frozen VIT, wave-to-vector, and BART backbone. And we are applying 5-fold cross-validation, 3 random seeds for reliability. So the results that we are getting, and it was published, it is that the handcrafted feature that gave us accuracy of 65.71, and the vision transformer BART and the AM rhythm that gave us the 74.29 accuracy. And for the MMSE score regression, we got the 6 RMSE value for the SVR VIT BART embedded model. The key findings that can be interpreted from here is that the AM rhythm spectrogram achieves the best accuracy, and it gives a 13.1% relative improvement over the MEL spectrogram baseline. So this means that rhythm feature is actually working while doing classification for the dementia speech data set. So handcrafted RFA features outperform 88-dimensional easy maps by 14.2% in classification accuracy. So that was another important improvisation done by the rhythm feature, that is the RFA feature. Then this is the first ever application of rhythm format analysis to dementia detection in the literature, and the embedding based SPR also achieves the best MMSE prediction. So these all codes are available, and if anyone interested, they can go for reproducing these models and build their own dementia detection classifier or any pathological speech detection, speech disorder classification or regression, if you are currently working on it, on such topic. Sorry. So I'm about to conclude. Hello, sir.
Yes, ma'am.
Yeah, so I'm about to conclude. If there are any questions, we can take up in between.
Yes.
Yeah.
Any questions from your side? Any faculty members, whatever things, or how we are going to plan? So you are planning to start the research in this particular area. Any queries you can ask now? Otherwise, ma'am will conclude. Ma'am, we have also lots of low resource languages are here because, as
Yes.
I had mentioned, we have around 2,000 plus from 70 countries. Foreign students are here. Most of the students are
Oh,
from the African continent. That is one,
great,
and we
great.
have also another tribal universities there. the world's first tribal university where 64 different languages, tribal students, around 30 to 40,000 number is also used. They are studying.
Oh, great.
If anyhow we are going to collect some data either in the recording format, 5 to 6 hours recording, then I think that part our faculties and our students and me also can give from our side.
Yes.
Then
Yes,
that will
yes,
be
yes,
better
definitely.
what we can do.
Definitely, sir. So that will be a very good work because it will also contribute to their community as well for
Yes,
building language technology. Because you see, we are the point from my presentation is that speech rhythm should be actually studied because it is the most natural. Phenomena that is embedded in the particular in our speech signal. So speech rhythm is very much less studied, and we also do not know much about the rhythm classes that about many languages, as you mentioned, these tribal languages and all. That is why many researchers are now interested on doing speech rhythm. And if anyone interested, I can provide reading materials and related database or codes, and we can work accordingly.
okay, ma'am. So I'll be in contact with you definitely.
Yeah, sure.
This is,
Yeah. So if
okay.
there is no any question, let me go to the slide of the summary slide. That is speech rhythm is quantified as time domain metrics and also the frequency domain RFA. And rhythm format analysis, which is the newer methodology, it is still under development. So we are working on the rhythm format analysis, and the final one, that is the Professor David is also of opinion that people should actually apply this RFA tool, so that it is an open research tool. Okay, so we should see how we can apply in various applications of our language technology. And for reference, this is the thesis. This is my thesis. It is available on Shodhganga and IIT Guwahati Open Library, and there are many papers. Anyone, if interested, they can contact me via mail, and I'll be happy to collaborate. Yeah. Thank you.
If anyone asks still, you can unmute yourself and ask some questions. Actually, they are muted. Any questions from audience side, participant? Okay. Okay, ma'am. Thank you very
Yeah.
much. I don't
Thank
think
you.
so. Any questions? Yeah, definitely, I'll be in contact with you and CCSR
Sure.
so that
Yeah.
we can do some work, collaborative work.
Thank you. Thank you. Thank you so much,
Thank you,
sir.
ma'am. Thank you.
Thank
Thank
you.
you.
Thank you. Thank you. Thank you, sir. We'll meet. Yes. Thank you.